very much, everyone. Let me share my screen. Okay. Okay, thank you very much for joining us. My name is Farah Majando. I'm the president for OneQuantum Africa. And we are bringing together the quantum community in the continent to learn about quantum technologies and figure out a role for ourselves as a continent and for individuals in the continent as well. What can they contribute? And also we want to stay in touch with experts in the global community so that we keep on learning and we keep in touch with this amazing technology as it evolves. So today we are going to hear from Scott Aaronson. He's the professor of computer science at the University of Texas at Austin. And I will be sharing a bit more detail about him later on when I introduce him to come over. So I want to share a few things up front about our community in Africa, our efforts, and everything else that we do at OneQuantum for those who have not been with us before. So the question that I always have to answer being a community leader in Africa is why we have to pay attention to quantum in Africa. So what we have done, this slide I'm sharing is courtesy of Lesedi Modize. She's a co-founder at Viability Quantum Technologies, one of the few startups that I know who are focusing on quantum tech in Africa, out of South Africa actually. So Lesedi also works for Sango Capital. So they deploy investments in Africa. They are a fund manager. And because of that, they've got good visibility of the startup ecosystem in the continent. And she did this work for us to just see where we think quantum technology, especially quantum computing, may have early benefits in the continent. So from that research, we see that obviously there are a few things that we have to accept about our circumstances here. The fact that we have got limited existing digital infrastructure. We've got structural challenges around ICT adoption. The sub-Saharan Africa especially continues to lag other regions in terms of digital access. And when we look at the investment case for quantum technologies in Africa, especially in quantum computing, we think that quantum hardware is far off down the line. But given that there are other regions that are making good progress and that quantum computing devices are available on the cloud, if that model is sustained, we are still going to be able to access the best technology from here and use it to solve problems that are relevant in the continent. One key opportunity for Africa from this research came from, I think with the thinking is that if we develop quantum software and quantum algorithm capabilities to solve problems that are relevant here, then we may be able to build a very strong foundation and case for quantum computing in Africa. And for that, consumer-facing African businesses are already implementing AI and complex optimization. And we feel that as they continue to want to improve capabilities, computational capabilities, they may find capable quantum computing hardware useful in that right. But today we've got an expert, Scott Aaronson, so he's going to help us to figure out what the role of quantum computers is, because there is a lot in terms of potential for these devices. But I guess we are going to have an opportunity to learn more about the areas where we have illusions and where we may have this opportunity coming. At OneQuantum Africa, so let me talk about OneQuantum Africa. OneQuantum Africa is a chapter of OneQuantum, which is a global platform that brings people together to collaborate, learn, and exchange in quantum tech. Our thinking is that if we focus on the 4 pillars that I have indicated on the slide, then we've got an opportunity of building a quantum ecosystem that allows each and every one of us to be successful faster. So under that structure, we've got communities, which is where we are at, where we come together and talk about quantum tech, bring experts from the global community, from the continental community, so that we learn more about quantum in the various regions. And we also get to have an opportunity for everyone who is interested in the space to learn and connect. We also have mentoring, which is where we support professional growth for people who want to build a career in quantum tech. We've got a careers aspect where we partner with what we call career partners, which are companies that are hiring in quantum tech, that are actively hiring in quantum tech, to learn more about opportunities in that space. so that we can develop the workforce in Africa. We've got a lot of young people, and one of the opportunities I see for people in the continent is where they, where we provide skills to the world. So that is one of the very important aspects of the work that we do. We've got careers, we learn more about the open opportunities and how to develop in terms of workforce development in order to take advantage of those opportunities. Then we also do work on projects which are relevant to the continent. We recently partnered with StrangeWorks to use their platform to streamline how we collaborate on projects that could be to allow people to learn more about quantum and develop hands-on skills, and also to solve problems that are relevant to the continent as is identified with our project leaders and the other experts in the global community whom we interact with. Our chapters, we've got a quantum chapter in Africa, we've got a quantum chapter for startups, we've got a women in quantum chapter that many of you may be aware of. These guys are actually going to deliver their 5th summit in July. I'm going to share details about that as we go. We've got a chapter from India, which had a beautiful, beautiful meeting over the weekend to bring the quantum community together in India. We've got Nepal, and for the quantum chapter in Nepal, they're actually going to run what they call the summer of quantum talks, and this is one of the first talks they are going to deliver. I'll share more details as we go. I also need to give you updates about what's happening, especially in Africa. So recently we had VISQ, which is a flagship project for the University of Witwatersrand, which is where I did an MSc in physics, experimental quantum physics. We're focusing more on Diamond, NV centers in Diamond as a platform for quantum information processing. So recently these guys launched, and this is going to be led by Alexander Forbes. Alexander Forbes was at the OneQuantum Africa Summit we hosted a few weeks back, and which we had the pleasure of hosting the global community and also being supported by companies like Honeywell. I want to share a few opportunities, and I just want to mention them briefly. All the opportunities are detailed in the newsletter, and I'll share the link. There are scholarships for people who are of African American origin, who you can take advantage of this opportunity to join the SQMS Research Center at FemiLab, the South African Theory school course, South African Theory school course offering as well, where the NITHEP, I think these guys are going to be teaching some courses in August, and this is an opportunity for people in South Africa particularly. Then Anisha Masti from Community is asking me to reach out to high scholars who are interested in quantum tech. They've got an opportunity for people to go on what they call the QBIS camp. It is a quantum bootcamp for students, and it's really, really beautiful to join this. It's the fee is $200 US, but she promised me that people in Africa, everyone who manages to apply will be able to access a scholarship. They've got a generous aid budget to cater for that. Let me now introduce briefly our speaker. So Scott is not an easy person to introduce. He's done a lot in the space, and some of you may know a lot about him. So I'm just going to give a brief introduction. Like I said, it's not easy to do justice to a person like him. Scott Aaronson is the David J. Bratton Centennial Professor of Computer Science at the University of Texas at Austin, and the director of its Quantum Information Center. Prior to this, he taught for 9 years in electrical engineering and computer science at MIT. His research interests center around the capabilities and limits of quantum computers and computational complexity theory more generally. Today, Scott is going to share with us his talk on quantum computational supremacy. Before I call Scott to come over, let me just tell you about what's happening next week. Next week, we have the pleasure of hosting Justin Perron. He has been with the NIST and completed a PhD at SUNY University at Buffalo. His research is in experimental solid-state physics, primarily focusing on silicon quantum electronics. I requested Justin to come and speak to us about quantum education and workforce training, because they recently hosted a workshop on quantum undergraduate education and scientific training. So he promised me that he's going to collect those results from this workshop and try to structure a talk that can help those of us in academia in the continent to think about how to introduce quantum education in universities. So thank you very much for this. I think I will stop sharing my screen and I will allow Scott to come through and share with us his talk on quantum computational supremacy. Scott, it's all yours. Looking forward to hear from you.
All right. Well, thank you so much. Thanks everyone for listening. Thank you, Farai, for inviting me for the wonderful introduction. So I want to tell you a little bit about one of the biggest pieces of news in quantum computing from the last few years, and this was the claimed achievement by Google and possibly others of a milestone that's been given this name of quantum computational supremacy. So what does that mean? What does it not mean? Now, I'm a theorist. I'm not an engineer. I don't actually build devices. I am pretty sure that this image here is not what a quantum computer really looks like. When you do a Google image search for quantum computer, it's one of the first things that comes up. Okay, well, let me start with the way I like to start this talk is what does quantum mechanics say about the world? And I think that physicists were managed to convince people for generations that it was really complicated. There's no hope of understanding it without studying physics for years and years. And actually what we've learned in quantum information science is that quantum mechanics is more like an operating system that physics runs on as application programs. It is simpler once you take the physics out of it. The way that we tend to think about quantum mechanics in this field is just as a certain generalization of the rules of probability themselves. Richard Feynman, who's one of the founders of quantum computing, used to say that pretty much everything about quantum mechanics is contained in this one experiment, the two-slit experiment. This is where I would take photons, let's say one at a time. I shoot them at a screen with some small holes in it, and I look at where that photon ends up on a second screen. And the first thing that we see is that the results are probabilistic, right? We can repeat the experiment with exactly the same initial conditions, and yet sometimes the photon will land in one place and other times in another place. Now, I rush to point out that by itself is not the strange part. If that was all that was going on, well, we use probability all the time, even in everyday life to model our uncertainty. It would be easy to invent a theory where each photon had, a little tag, let's say a little ID tag on it that we don't see, that somehow secretly determines which way it goes. The weird part is what we have to do in order to calculate the probability. Okay, and what we see is that there are certain spots, let's say on the second screen, where the photon has a lower chance of reaching those spots if both slits are open than it has of reaching them if only one slit is open. Okay, so to say that again, by increasing the number of holes, by increasing the number of paths that the photon could take to reach a certain spot, I can decrease the chance that it gets to that spot. Okay, and this is really the new part. Okay, and physicists saw one phenomenon after another like this a century ago, until finally they invented a mathematical framework to account for it, and that framework sort of generalizes the normal rules of probability. It says that to each way that the photon could go, we have to assign a number called an amplitude. And amplitudes are related to probabilities. The larger the amplitude for some configuration, the more likely we will be to find the photon in that configuration. but amplitudes are not probabilities. Okay, a probability is always from 0 to 1, right? You'd never have a negative 20% chance of something happening. Okay, but amplitudes can be positive or negative. In fact, they're complex numbers. And the rule is, if first of all, the total amplitude for a thing to happen is the sum of the amplitudes of all of the different ways that it could have happened. Okay, so if an event could happen one way with a positive amplitude and another way with a negative amplitude, then those two contributions can, as we say, interfere destructively and cancel each other out, so that the total amplitude will be 0 and that event will never happen at all. Okay, the probability that I see something is equal to the square of the absolute value of its amplitude. Okay, so higher amplitude means higher probability, but if some amplitudes are positive and some are negative, or they're pointing in different directions, they can cancel each other out. Okay, that is the new thing. That's the thing that doesn't happen with conventional probabilities. And everything you'll ever hear about quantum mechanics, whether it's entanglement or quantum computers for that matter, they're just more and more applications of this one change to the rules of probability. Okay, so let's talk about quantum computers now. A quantum computer is just a computer that a normal computer is made of bits. It could have let's say some number n of bits, and so the computer is in one of 2 to the n power different states, right? One for every possible string of n bits. Now, the difference with a quantum computer is that it can be in what we call a superposition state, which simply means that we assign one amplitude to every possible classical configuration of the computer. Okay, so the state of our computer will be a list now of 2 to the n power amplitudes. Okay, one complex number representing every possible sequence of bits that we could see when we looked at the computer state. Okay, but at this point, I have to caution you, because almost every popular article that's ever been written about quantum computing over the last 25 years, it will sort of explain maybe what I just said, and then it will take a wrong turn. It will say, well, so the point of superposition is just that a quantum computer can do everything at once. So it will say a quantum computer would just try every possible answer in parallel, in superposition, maybe even in different parallel universes. And this is the explanation of how a quantum computer would solve, the traveling salesman problem, or solve other famous hard problems, breaking cryptographic codes, just by trying every possible key in parallel. Unfortunately, it's not that simple. Okay, that's not how it works. And let me tell you what the problem is. With a quantum computer, you can create a superposition over all the possible answers to your problem, even if there are exponentially many of them, like 2 to the 1,000 power, more possible answers than would fit in the entire visible universe. Okay, you can do that. That's even an easy thing to do with a quantum computer. So, you have this branching tree of possibilities, like this binary tree that I've shown here, and you can easily assign an equal amplitude to every possible solution. The trouble is that for a computer to be useful, at some point you have to measure it, you have to observe, and the rules of quantum mechanics tell you that if you just measure an equal superposition over all the answers, not having done anything else, then all you'll see will be a random answer, a completely random string. And of course, if you just wanted a random answer, well, then you could have picked one yourself with a lot less difficulty. You could have saved billions of dollars, or whatever it took to build the quantum computer. So for this reason, the entire hope of getting a speed up or an advantage from a quantum computer is to exploit the way that amplitudes, being complex numbers, are different from probabilities. Okay, so with every quantum computation, the idea is to choreograph a pattern of interference so that for each wrong answer, each answer that you don't want to see, you get destructive interference. Okay, some of the paths leading to that answer have positive amplitude, others have negative amplitude. They mostly cancel each other out. Whereas for the right answer or answers, for the ones that you do want to see, you want constructive interference. Okay, you want all of the paths leading to those answers to have amplitudes pointing in the same direction. Okay, so that they add up constructively. If you can arrange that, then when you measure at the end, you will see the right answer with a large probability. If you don't see the right answer, you can always repeat the computation from the beginning until you do. But the tricky part is, you need to boost the amplitude on the right answers by using interference. You need to do that even though you yourself don't know in advance which answer is the right one. Because if you already knew, then what would be the point of using the quantum computer? And you need to do this quickly, faster than you could just find the answer using your classical computer. Okay, so this is why designing quantum algorithms is so hard, because you have to meet all of those requirements. You're competing against the best that people can do with conventional computers. If you can't beat that, then there's really no point in using the quantum computer at all. So nature has given us this really, really strange hammer, of this ability to create these interference patterns of amplitudes. And the task of quantum algorithm designer is to sort of find nails that hammer can hit. Okay, and a priori, there didn't have to be any interesting nails that it could hit. Okay, the original application of quantum computers that Richard Feynman and David Deutsch talked about 40 years ago was simply simulating quantum mechanics itself. Okay, now that's still probably the most important application of quantum computers that we know about today. As obvious as it might sound, right? That is something that could have uses in designing new drugs, designing materials, high temperature superconductors, all sorts of things like that. And but what was not obvious, what people only started figuring out in the 1990s, was how to use a quantum computer sometimes to get speed ups even for purely classical problems that have nothing to do with quantum mechanics. Okay, but that is a very special thing. That's a very hit or miss business, I would say. Okay, so I haven't said anything yet about the engineering problem. How do you actually build a quantum computer? As many of you might know, there are lots of approaches being pursued in parallel right now. A qubit, the basic building block of a quantum computer, is just a bit that can be in a superposition of the 0 and the 1 states. So, has an amplitude to be 0 and an amplitude to be 1. But that says nothing about how a qubit is to be physically realized. Okay, and just like a classical bit, might be realized using a transistor, but it might also be realized, using an abacus or, using a magnetic tape or any number of other ways. So, a qubit could be realized using many different kinds of quantum systems. And we don't know yet, which of any of these proposals will be, the right way to go as an engineering matter. So, one idea is to use the spin states of atomic nuclei, like ytterbium ions, and you trap them in a magnetic field. You manipulate them using lasers, and you can get them to interact with each other in a way that will perform your quantum computation. This approach is being pursued by a startup company called IonQ, by Honeywell, and by some others. You could also use neutral atoms the group of Misha Lukin at Harvard has been doing that. You can use photons to encode qubits. Okay, try to build a quantum computer out of light. There's a group in China that's been doing that. Also, a startup company called OneQuantum in Palo Alto that is trying to build chips for optical quantum computing. There is one approach that is, I would say, speculative, even by the standards of quantum computing, which requires creating a new state of matter that has never been seen in nature. And this is called the topological approach, or the non-abelian Anion approach. Now, Microsoft has placed a huge gamble on that approach to quantum computing. And it has some sort of natural error resilience properties where, if it worked at all, then, on paper, it looks like it could scale much better than any of the other approaches. But so far, they have not yet succeeded at creating even one topological qubit. Okay, whereas with the photonic approach, with the trapped ion approach and others, people are now routinely doing experiments involving dozens of qubits. And they can create very complicated states, what we would call entangled states, involving all of the qubits together. They can do it in a controlled way. When this was none of this was true when I joined the field. Let's say 20 or I guess 22 years ago. This was all on paper, or it was experiments involving maybe 1 or 2 qubits at a time. Today, people really can do experiments with dozens of qubits, and actually see some of these phenomena for real. Okay, now the approach that is maybe the furthest along right now is called superconducting qubits. This is being pursued by Google, by IBM, by a team at Yale, and by others around the world. And in the superconducting approach, so your qubits are actually enormous by the standards of qubits. They can be almost big enough to see with the naked eye. Okay, they are basically coils that a current can flow around, and it can flow in 2 different states. One of them encoding a 0 and the other encoding a 1. What you do is you take this chip with the coils on it and you put it in a dilution refrigerator. That's this thing down here, which looks like an upside down wedding cake. And you cool the chip to nearly absolute 0, usually about 10 millikelvin, something like that. And that causes the currents to superconduct. Okay, now superconductivity is a quantum phenomenon, right? And it allows the currents to flow in superpositions of the 0 states and the 1 states. We then have some classical electronics outside of the dilution fridge that we can use to actually control the qubits, tell them what operation to do when. We use a component called a Josephson junction to do that. And each qubit is able to talk to its neighbors. They are laid out in roughly a square grid, and they can interact with each other in a controllable way. Okay, so so these are a bunch of maybe what look like promising approaches to building quantum computers. But you might say, why is it so damn hard to actually build a quantum computer with 1 million qubits? The kind that we dream about, the kind that could really give us a general window into simulating quantum mechanics, also breaking cryptographic codes, and doing other exciting things. The central difficulty in building a quantum computer has been understood from the very beginning, and it's called decoherence. Okay, I mentioned before that when you look at a qubit, you only get a single sample. You get one outcome, right? If I look at a qubit in a superposition of the 0 and 1 states, I force it to decide whether it wants to be 0 or 1. It picks each one with a probability, which is just the squared absolute value of the corresponding amplitude. And whichever choice it makes, it then sticks with it forever. Okay, so measurement is a destructive process, right? And it is irreversible, at least as far as anyone knows today. So now, crucially, it doesn't have to be a person who is looking. Okay, so if there is any interaction with, the radiation in the room or with nearby warm objects or anything like that, which causes the information about whether a qubit is 0 or 1 to leak out into the environment, to get recorded by the environment, then the effect on the qubit will be exactly as if someone had measured it. Okay, it will then revert to being a classical bit. You will no longer be able to see interference between the 0 state and the 1 state. This is called the decoherence problem. Okay, what it means is that if you want to build a useful quantum computer, then you have to keep the qubits almost perfectly isolated from their environment. Okay, they have to not be leaking anything into the rest of the world, but they can't be perfectly isolated because you have to actually do operations on them. You have to tell them which operations to do when. Okay, this is such a severe problem that there were distinguished physicists in the 1990s who said building a quantum computer looks fundamentally impossible. It looks like building a perpetual motion machine, or faster than light communication or something like that, right? Like it just there must be a law of physics that will prevent this from working, because you will never perfectly isolate qubits well enough to do all of this computation on them. Now, the discovery that changed most people's minds was a really fundamental new idea in the mid to late 1990s. And this was called quantum error correction and quantum fault tolerance. And basically what was discovered was that to build a useful quantum computer, you don't have to get the interaction with the environment all the way down to 0. It is enough to make it very, very, very small. Okay, once the rate of decoherence, in each qubit becomes low enough, then there are these very clever quantum error correcting codes that can be used to basically take a single qubit of your quantum computation, a single logical qubit, as we'd say, and then encode it into an entangled state of dozens or even hundreds or thousands of physical qubits. Okay, and does so in such a way that even if any small fraction of those qubits are to leak their states into the environment, in fact, even if every one of the qubits is slowly leaking its state into the environment, we can dynamically monitor for that, and we can correct it as it is happening, okay, and thereby protect the encoded qubits, the quantum information that we care about, for an arbitrarily long time. The problem is, fault tolerance itself, requires very precise control over the qubits, right? So there is a threshold, sort of a physical error rate, where once you get below that threshold, then error correction can be used to make the effective error rate lower and lower and lower, and then effectively keep your qubits alive for an arbitrarily long time. Okay, but if you are above that threshold, then all of the error correction that you do is just making things worse rather than making them better. Okay, and so people realized this 25 years ago, and the threshold at that time was maybe a factor of 1 million, away from what the experimentalists could actually achieve in the lab. That was about the situation at the time that I joined this field as a young student. And today I would say, the experimentalists are still not at the threshold where fault tolerance, will give a net win. But I would say they are only about a factor of 100 away, depending on how you measure it. Okay, so things have improved by just many, many orders of magnitude since 20 years ago. But they are not there yet. Okay, so and this is the reason why all of the quantum computations that we read about in the press, and in public announcements. They are sort of for artificial benchmarks, for artificial demonstration problems, or they're stuff where people claim to solve a useful problem, but then if you look at it carefully enough, typically they are not solving that problem any better than you could have solved it with a classical computer, right? So people, unfortunately, people have learned by now that if you say that you used a quantum computer to do such and such, journalists will not ask too many questions about it, right? They'll say, oh, quantum means that no one will understand it and it's mysterious, so we should just repeat whatever is said. And so you can use a quantum computer to do something that that someone could have easily done with their laptop, and people will still write about it as if you had beat any classical computer. Okay, but what if we want to do something that's more serious than that? So we want to actually beat classical computers. So this brings me last to this topic of quantum supremacy. And this is just a name that was given in 2012 by the physicist John Preskill for the first demonstration where a quantum computer could do something, some well-defined task faster than we know how to do that task with any existing classical computer in the world. Okay. Now notice that I did not say a useful task. Okay, so it doesn't have to be useful. It can be a completely useless benchmark, but we want to be confident that we are seeing a real quantum speed up, even compared to the best that a classical computer could have done, without having to tie the classical computer's hands behind its back in some kind of cheating way. Okay, now I like to joke that for me, this has always been the #1 application of a quantum computer, just to disprove all of the people who said that a quantum speed up was not possible, right? To me, all of the other stuff that people talk about, whether that's simulating quantum mechanics or breaking cryptographic codes, or maybe eventually getting some modest speed ups for optimization and machine learning problems, all of that is kind of like icing on the cake. But for me, just to show scientifically that quantum speedups are real, that we can really achieve them with technology that exists on Earth, that's at least as exciting as, let's say, to find the Higgs boson, to find gravitational waves, or any of the other great experiments that we see in physics. Okay, so now we come to the question: how does one achieve quantum supremacy? In some sense, we've known the gold standard for a long time. The gold standard is Shor's algorithm. This was the famous discovery 27 years ago that first brought quantum computing to wider attention. And what Shor showed is that if you could build, say, a fully scalable, error-corrected quantum computer, then you could, with effectively perfect qubits, then you could use it to factor large numbers. You could factor a number with n digits using a number of steps that's only grows like n squared, roughly. Whereas the best classical algorithms that we know need a number of steps that grows exponentially with n, actually with the cube root of n. Okay. This made a lot of people interested in quantum computing, including intelligence agencies, because, for better or worse, most of the encryption that we currently use to protect the internet is based on codes such as RSA or Diffie-Hellman, all of which turn out to be breakable using Shor's algorithm. Okay, so this would really force, a huge change to the way that we protect commerce on the internet. Okay, but as I said, building a scalable quantum computer still, that would be able to run Shor's algorithm, still, even in 2021, looks to be some ways off. So so a decade ago, some of us, were realizing that we would be in this situation, and we were thinking about, is there a more direct way to achieve quantum supremacy? Could it be done, not using 1,000,000 qubits, not using error correction, but even using 50 or 100 noisy qubits, such as, we might have available, in the reasonably near future. And so some of us studied this question. So my student Alex Arkhipov and I wrote a paper about it, about one particular proposal for how to do this, which was called Boson Sampling. And others at the same time, like Bremner, Joza, and Shepard, had related proposals. And this sort of crystallized an understanding that if your goal is just to demonstrate quantum supremacy, then you don't have to try to solve a problem like factoring, that has a single right answer, right? There are actually a lot of advantages to switching your attention to what we would call sampling problems. Okay, these are problems where the desired output is a sample from a probability distribution, say over strings of n bits. And, so the computer just has to output a sample with something like the appropriate probabilities. Okay, so there are many, many possible valid outputs, right? And your computer, over its whole lifetime might never even produce the same output twice. Okay, but the question will be just, is it more likely to produce the outputs that have the higher probabilities? So is it sampling from the correct distribution? Now sampling problems have a long history in computer science. Knuth even talks about them in, The Art of Computer Programming. But for our purposes, sampling problems have a couple of really big benefits as a way to demonstrate quantum supremacy. Okay. Now the first benefit, the one that sort of led us to study sampling problems in the first place, was that if you just want theoretical evidence that you are solving something that is hard for a classical computer, then it turns out that there are very direct ways to get that evidence for sampling problems that we don't know how to get for problems like factoring. Okay, so we, Arkhipov and I, were able to prove theorems that said, for example, here is a probability distribution that could be sampled using a very rudimentary type of quantum device, but which has the property that if there were a fast classical algorithm that could sample from that same distribution, then this would have dramatic consequences for classical theoretical computer science. It would mean something like, the collapse of the polynomial hierarchy. If you don't know what that means, well, if you've heard of the P versus NP problem, right? It would be the polynomial hierarchy is an infinite hierarchy of which the first two levels are P and NP. Right? So the most dramatic collapse would be if P equaled NP, okay, which is something that hardly anyone believes would happen, right? And the whole point, if you prove that a problem is NP complete, then the whole point is that you cannot solve that problem efficiently unless all of the NP problems could be solved efficiently. Okay, the collapse of the polynomial hierarchy is not quite as dramatic as P equaling NP, but it's almost as dramatic. We showed that if you could efficiently simulate these sampling-based quantum supremacy experiments using a classical computer, then the polynomial hierarchy would collapse to the third level. Okay, so and that's arguably stronger evidence that the problem is hard for a classical computer than we have that factoring numbers, for example, is hard for a classical computer, which is, all of these are statements that no one has proved, right? We're just basing off of, how strong is our belief that these problems really are hard for classical computers. But then a second advantage was that, in order to sample from these probability distributions, it became clear that you did not necessarily have to build a full quantum computer, right? So the type of device that Arkhipov and I were led to study, just for theoretical reasons, was an optical device where you would generate a bunch of photons, single photons, let's say. You would send them through a network of beam splitters, so mirrors and beam splitters that can split a photon into a superposition of going this way and going that way. And then at the very end, you would have detectors that at each port, would measure how many photons are there. Okay, and that's all you had. So this is not a universal quantum computer. We don't think, in fact, we don't even think it's a universal classical computer. And yet, nevertheless, it can sample from these distributions where we could give strong evidence that they are hard to sample using a classical computer. Okay, so that, along with the other works along these lines, that then started a quest over the past decade to actually demonstrate quantum supremacy in the lab. Okay, and this leads me at last to Google's demonstration of quantum supremacy. In late, which they announced, or which actually leaked to the press in late 2019. Okay, and so they decided that they wanted to do something like boson sampling, but which was more adapted to their hardware. Okay, so they, as I said, were building superconducting qubits. So they built a chip called, which they called Sycamore, which has 53 qubits on it. If you're wondering why 53, they built 54 qubits in a roughly rectangular array, and then one of them didn't work. Okay, so they have these 53 qubits, and they apply basically a random sequence of operations to them, which and then they measure each qubit to see whether it's 0 or 1. And each time they do this gives them a sample from a probability distribution over 53-bit strings. Okay. Now the number, how large is that distribution? Well, the number of possible 53-bit strings is 2 to the 53 power, which is about 9 quadrillion. Okay, so as far as at least Google knew at that time, the best classical algorithm to simulate this experiment, could need something like 9 quadrillion steps. Okay, because you could write down the entire quantum state, in a memory, or you could calculate each amplitude by adding up all of the different contributions to it. But either way, you're using exponential time. So this was the basis for their claim of quantum supremacy. Now, there is a lot of noise in their system. So I would say that each time they make a measurement, there's like a 0.2% signal, 99.8% noise, which sounds bad. But the good news is that the chip is very fast. It is able to take each sample from the distribution in only about 40 microseconds, which means that in a few minutes, you can take millions of independent samples. And that is then enough to do statistics and extract a signal from the noise. That is exactly what Google did. So yeah, this slide is just a little bit more, details about, the experiment. Now, a crucial question is, suppose you do this experiment like they did, and then you get all these outputs. There are a bunch of 53-bit strings that you saw when you looked at the qubits. How do you verify the experiment? How do you check that your quantum computer actually did what it was supposed to do? Because the trouble is, all you see are these samples, right? There's no one right answer. So in order to verify the answer, have to do some kind of statistics on the samples that you saw. You have to apply some sort of test to the samples that the real quantum computer can pass, but that a classical computer should not be able to pass in any reasonable amount of time. Okay, so my student Li Ji Chen and I did some theoretical work on what could such a test be. And then Google used a version of that test, but they called it the linear cross entropy benchmark, or linear XEB. Okay, and the test was actually very, very simple. It was as follows. They take each of the samples that they see, they calculate using a classical computer and using sort of heroic, amounts of time. It might take, weeks and weeks using, a million parallel classical computers. But, if you're Google, then you have that, right? And so then you calculate, well, with an ideal quantum computer, what would have been the probability of each of the samples that I saw? You then take all of those probabilities and you sum them all up. Okay, and you say that the test passes if and only if that sum exceeds a particular threshold. Okay, so that's the test. So then, what is that threshold? Well, if I was, suppose that we had no quantum computer and we were just picking the samples completely at random, then I would expect each sample to have a probability, according to this distribution, of about 1/2n on average. So if I added up k of the samples, I would get about k/2n. Now, if I have a perfect quantum computer without noise, then you can prove that in that case, the value of this sum would be about 2k/2n. So exactly twice the sort of trivial baseline value. Okay, and so now the question for Google's experiment was, could they show that they could achieve a value of this sum that is not necessarily b = 2, not necessarily the ideal value, but at least is better than b = 1, which would be just the trivial classical value. Okay, so bottom line, in their experiment, they reported a value of this number b, which was about 1.002. Okay, so just slightly above the classical value. Okay, but that is, at least according to the theoretical work, that is good enough for quantum supremacy, because they were able to prove statistically that 1.002, really is larger than 1. It is not just a measurement error or anything like that. Okay, now IBM and others published what they viewed as rebuttals of Google's quantum supremacy claim, and they said, well, we don't think Google really has achieved quantum supremacy because what IBM said was that, well, if you use the largest supercomputer, which is currently on Earth, which is called Summit, it's at Oak Ridge National Labs in Tennessee. And it fills the area of 2 basketball courts, and it has 250 petabytes of hard disk space. Okay, then they said this machine is, just barely, but is big enough to actually take 2 to the 53 amplitudes, 9 quadrillion complex numbers, and store all of them explicitly in memory. Okay, just store them all to hard disk. Google had been thinking that you have to store the results in RAM, and then there wouldn't be enough with any computer on Earth. But, okay, if you use Summit, you could store them all in hard disk. And then IBM estimated that you could then simulate Google's chip in only 2.5 days with a classical computer. Now, you'll notice that that is more than 3 minutes. So the quantum computer is still a lot faster. Okay, but it's a lot less than Google had estimated a classical computer would need. So, so the quantum supremacy is by a smaller factor. Now, IBM did not actually do this calculation. It's not cheap or easy to get that kind of time on the biggest supercomputer on the planet. Okay, my own view was that this was sort of a backhanded compliment. Like, if this is what it takes to simulate, the Google chip, then it is clear that, however you define quantum supremacy, either it's been achieved or else it is on track to be achieved within the next couple of years, right? It's kind of like the IBM versus, the Kasparov versus Deep Blue chess match in the 90s, except with the, great irony that IBM is now in the role of Gary Kasparov, right? Is now, then go with heroic effort, maybe I can match this machine, for now, but then, or almost match it, but then clearly, the machine will win in another year or two. Okay. So since then, there have been other proposed simulations published for Google's Sycamore chip. Some of them, that would need much less memory and just a similar amount of time. But one can also evade those simulations by just changing the verification test that's being done. So instead of that linear cross entropy test, if you additionally test that the outputs are the sampled strings are far from one another, then that would defeat these tests. Okay, so the theoretical work that we did, a few years ago, most of it was aimed at, well, is there some much faster way to simulate these quantum supremacy experiments using a classical computer, right? That is the sort of thing that, if true, I think really could, permanently kill Google's claim of quantum supremacy, right? But, as far as we know, all of the currently known classical simulation methods, take time that scales at least exponentially with the number of qubits, like at least like 2 to the n power, where n's the number of qubits. And there are different trade-offs between the time usage and the memory usage. And, and we explored those trade-offs. But the main thing we wanted to do is give some theoretical evidence that that there really is a 2 to the n barrier here. That is, that any classical algorithm really will need, something like 2 to the n time in order to spoof this linear cross entropy test. Okay, we don't want to say that it is merely a matter of just insufficient cleverness right now, right? We want to say that it's impossible to efficiently simulate this experiment using a classical computer. Now, the trouble is that theoretical computer science is just not in the state right now to be able to prove that sort of thing as a theorem, right? We haven't even proved that P is not equal to NP, right? So, these are just incredibly hard mathematical problems. But what we can often do is pass the blame to somebody else. That is, we can say, well, if you had a fast algorithm for solving this problem, then there would also be fast algorithms to solve a lot of other problems, that people care about and that would seem very surprising. This is called a reduction argument for hardness. And this is to a great extent, this is what modern theoretical computer science is based on. And so we were able to give some reduction arguments for the hardness of spoofing this linear cross entropy test using a classical computer. Okay, so we said that if you had a fast classical algorithm to spoof the test, then you could turn it into a fast classical algorithm that would take a random quantum circuit and that would estimate the probabilities of specific outputs much faster than we believe is possible. So that's it's not as strong evidence as we would like, but it's some evidence that there is nothing special about this linear cross entropy benchmark that is making it super easy to spoof. Okay, now just half a year ago, late 2020, there was a second announcement of quantum supremacy. This was by the group of Chaoyang Liu and Jianwei Pan at USTC in China. And they actually used Boson sampling, which was my and Alex Archipov's original proposal for how to achieve quantum supremacy. They built a giant network of beam splitters on an optical table. There's a photograph of it, and they passed about 50 to 70 photons at once through this system, and then they measure, where the photons land. And they even have a much larger number of possible outputs than Google had. Google had like 10 to the 16 outputs. This newer experiment has 10 to the 30th possible outputs. Unfortunately, in order to do this experiment today, they had to cut some corners. So, there's about 70% of the photons get lost on the way through. Only like 30% of them get detected. Also, instead of using single photon states, they use a different kind of state called Gaussian states. Instead of having like an enormous number of modes, places where the photons could be, they have a smaller number of modes. It now looks like, because of those corners that were cut, that there is actually a fast way to simulate this experiment using a classical computer. Okay, that is what the most recent research, like as of a few weeks ago, is saying. Okay, but this is a perfect example of what is so tricky about quantum supremacy claims, right? It's not like landing on the moon where you just do it and then it's clear to everyone. It is all about beating a classical computer. Okay, and classical computers can also fight back, right? And so in order for your claim to be convincing, you have to publish all of your data. Everyone has to be able to try and replicate your results using a classical computer. And only if they can't do it for a significant amount of time are we really convinced that this is quantum supremacy. Okay. This experiment is clearly a big step forward in any case, but it looks like it's not yet there in terms of getting quantum supremacy via boson sampling. I hope that will be done in the fairly near future. Now, until very recently, people said, these quantum supremacy experiments based on sampling, they might be interesting theoretically, but it's clear that they have no applications in and of themselves, right? Because, they're just sampling random numbers, and who cares about random numbers, right? It's, you don't need a quantum computer, as I said before, to generate random numbers. Okay, well, a few years ago, I had an idea which might change the situation. What I realized was that, if you do these quantum supremacy experiments based on sampling, well, it's not just that you're getting random outputs, it's that you're getting outputs that you could prove to a skeptic must have been generated randomly under some computational hardness assumptions. Okay, so you could be interacting, let's say, with Google's quantum computer over the internet. You could challenge Google's quantum computer, say, output from the, give me some samples from the output distribution of this quantum circuit. Do it now. Do it within the next second, right? And let's say that Google sends you back those samples within the next second. Now, let's say you then slowly, at your leisure, you verify those samples by doing like the linear cross entropy benchmark, something like that, and suppose that they pass the test. Okay, then what I can show is that then under some computational assumptions, even assuming that Google has a quantum computer, the only way they could have generated the samples that quickly that passed the linear cross entropy test is to generate them, in the appropriate way, meaning with a lot of real randomness, which ultimately comes from, the randomness of measurement in quantum mechanics. Okay, which means, now you have a certification that these bits, were generated far away, really were generated randomly. They were not generated in a way that was secretly deterministic. Okay, now that could have a bunch of applications. So, for example, proof of stake cryptocurrencies, which are like, like the next generation Ethereum, which are supposed to be much more energy efficient, much more environmentally friendly than Bitcoin. These require an enormous source of randomness that is trusted by everyone. Okay, because they're constantly running a lottery to decide who gets to add the next block to the blockchain. Okay, so it could be usable for that. But there's a lot of work needed to make this practical. There's mostly because the verification itself right now is too expensive. We need a faster way to verify the results. But nevertheless, Google is actually working now to demonstrate this scheme. Okay, so there are a lot of exciting places to go next. As I just said, I think maybe the biggest problem is, can we get quantum supremacy on existing quantum computers or on the ones we're going to have in the next few years, but in a way where the results can actually be efficiently verified using a classical computer. So where you don't have to do these gargantuan classical computations, even just to check the quantum computation. Can we replicate quantum supremacy in other hardware platforms? Do it in a better way with boson sampling. Do it using trapped ions. Do it using with lower error. Can we design new classical simulation algorithms that would kill these quantum supremacy claims? Or, in the other direction, can we give better theoretical evidence for hardness? And finally, can we take something like my scheme for certified randomness, and can we make it more practical? If we did, then that could be actually the first realizable application for a quantum computer, like something that could be realized using hardware like what Google already has. So to conclude, Google may have achieved quantum supremacy for sampling tasks, building on a lot of theory that we did over the last decade. Even if true, it leaves the huge challenges of scalability and fault tolerance. But I think it's already enough to refute those who said that quantum speedups were impossible. It was thought obvious for years that sampling-based quantum supremacy experiments had no applications. Things like the certified randomness protocol might change that, although a lot of challenges remain in making it practical. So with that, thank you for listening. I am sorry that I went a little over time, but I'm very happy to take any questions.
Thanks, Scott. That was really a wonderful presentation. And yes, indeed, there are a number of questions in the chat.
Sure.
So if perhaps you can turn your attention to the chat so that I don't have to read them.
Do you want me to just look at the chat window? Do you want me, where do you want me to start?
I think the questions start on what? That was at 3:45. If you can trace the chat back there.
Sorry, do you want me to start at the top and scroll down?
Sure. So it will be 3:45.
All right. Okay. Yeah. So the topological approach to qubits is the reason people cared about Majorana fermions so much was that if you could create Majorana fermions, that is a stepping stone toward creating a topological qubit. Right? It's not enough by itself, but it would be a big step in that direction. Unfortunately, there was a big paper in Nature a few years ago that claimed the detection of Majorana fermions, and just a few months ago, that paper was retracted. Okay, it looks like they did not actually detect it. The non-abelian Anion approach to quantum computing, it would take a long digression to try to explain that. But basically, you create a new state of matter where where you in a two-dimensional medium where you have some excitations, quasi-particles that behave not as bosons and not as fermions, but as a third type of particle, which is called an anion, and that have more complicated statistics. And it was proved by Alexei Kitaev and Michael Friedman 20 years ago that if you could just braid these anions around each other in an appropriate pattern, then that is enough to do a universal quantum computation. Okay, the trouble is to actually make these anions and control them. That is the part that no one has demonstrated yet. Okay, so now next question is from Tamaz Varga is, Scott, do you expect there will be genuinely quantum applications that aren't about speedups? So the one use of a quantum computer that people have thought about, that is not about speedups is really, about various cryptographic things, that have to do with the fact that, you cannot copy the state of a quantum computer, right? You are limited in what you can learn by measuring, a quantum state. And so you could imagine things like quantum money, so you'd, and if this worked, this could just completely replace Bitcoin, right? You wouldn't need a blockchain. you could just have a quantum state, that anyone could verify as being legitimate money, but which you would not, no counterfeiter would easily be able to make a copy of. If they tried to make a copy, they would have to make a measurement that would just destroy the state, right? So, I have some papers like from 2009 and 2012 about proposals for how to do quantum money that anyone could verify, and also about a related problem, which is quantum copy protected software. So can you have a quantum state that would let you compute a function, but where you could not create copies of the state to give to your friends that would let them compute the same function, right? There's also what's called, blind quantum computing. This is a proposal from maybe 14 years ago, where you can give someone a quantum computation to perform, but you can give it to them in an encoded way. If you send them qubits that are rotated by angles that they don't know, you can have them do a computation for you where they don't know which computation they were doing for you. That could be useful for secure cloud computing, for example. So those are some applications of quantum computing that are not about speed ups. You'll notice that they're all sort of about cryptography in one way or another, about preventing someone from learning something by accessing the quantum state. Okay. Other than that, I think, if you don't care about speed ups, then just use a classical computer, right? So let's see. Supercomputing, comment on the rise of supercomputing, quantum computing hubs. I have to confess that I don't know what those are. So maybe I'll pass on that. How do I pick issues to speak about? I mostly just try to speak about what I know, right? I try to speak about what I have worked on, or at least what is in the intersection of what I have, personally worked on and know something about, and what other people might be interested in, right? So and that's why, like, for the past couple of years, I've been giving talk after talk about quantum supremacy experiments. There are other interesting things to talk about, but there are probably just other people who are better than me to talk about them. How bad was the setback faced by? I don't really know, to be perfectly honest, right? I think that Majorana fermions should completely be creatable, should be detectable. It will just take another experiment to do that, right? I don't think that there was anything wrong, with the ideas, with the principle. There was something wrong with the execution of the experiment. Let's see. Some suggest that quantum startups should be set up more like biotech with a pure R&D focus to avoid overpromising. What do you think? I would tend to agree with that, at least for now, at least for like this stage in the development of the field. I think that if a startup, can be in a situation where, it has, venture capital, and it is able to sort of pursue long-term projects, then, it is more able to avoid the temptation to sort of misrepresent the state of the field to the public, right? I think what we've learned over the past decade is that there is an enormous temptation for quantum computing startups to say to the public or say to potential customers and investors, look, we are getting, amazing speed ups right now for your problems, for the traveling salesman problem, for industrial optimization, for deep learning, for pick whatever problem you most care about, and that's what quantum promises a huge speed up for, right? And and those of us who work in this field kind of know that 95% of that is bull, right? It's it's quantum algorithms that no one has analyzed, that we have no idea if they'll actually deliver such advantages. The best we can say really is that no one has proved that they can't deliver an advantage. but but there's not really a positive case that they can. I mean, especially for things like machine learning. And furthermore, to the extent that they can, those are not speed ups that we expect to be realized, in the near future. You might need like a full fault tolerant quantum computer that would be capable of running Grover's algorithm. And then if that's what you're doing, if it's Grover's algorithm, which is the square root speed up, then we don't expect to see a benefit over a classical computer for quite a long time. Okay. So there's a question: how do we convince business of the viability of quantum technologies? I mean, for me, that's kind of the wrong question, right? That's not the question I ask. Right? I try to just tell the truth, whatever the truth is, right? And I think that business is massively interested in this subject right now, right? And the question is, how do we take that interest and how do we channel it into the things that are most likely to lead to genuine advances, that are not just smoke and mirrors. What does entanglement in time mean? The truth is, I've never understood that myself. If someone else understands, the concept of entanglement in time, then maybe they should explain it to me. Let's see. Can I talk about tensor networks? They are very important. Tensor networks are a tool for representing quantum states on a classical computer that works best when the states have a limited amount of entanglement. And they're a tool that can be used for simulating quantum circuits classically, and that has been explored for simulating, for example, the quantum supremacy experiments. I did mention something about that in my talk, right? That these methods are now being used to try to simulate the Google experiment, but to the extent that they work, they can also often be evaded, either by just increasing the depth of the quantum circuit. So if Google could just increase the reliability of their gates a little, they could do higher depth, and that will start to throw off these tensor network methods. And even with the depth they have, which is about 20 layers of gates, the tensor network methods, they can produce a lot of samples, but the samples are all very correlated with each other if you want to produce them quickly. So if you just check that the quantum computer's outputs are sufficiently uncorrelated with each other, then that is enough to throw off those methods.
That's okay, Scott. We may not finish all of them. I wanted to take a question from Alexander. He's raised his hand. May you please come through? Then I go with Scott through a lightning round for the fun of it, and then we end the meeting. Thank you.
Okay.
Hey, Scott, I have a question. Hi.
Sure.
You mentioned randomness verification, right? Mm-hmm. Do you have anything to say about that? I actually was doing research in this area by myself and had some approach because all existing methods are very complex and requires a lot of time with no certain way out.
Yeah. So I mean, it's not okay. Now I mean, if your goal is sort of random bits that are certified that everyone believes in, right? There are many ways that you could imagine doing that. You could ask everyone to point their telescopes at the sun and look at the pattern of granules that's forming on the surface of the sun. That's something that's plausibly unpredictable, and that's also the same for everybody, right? You could look at the last digits of the Dow Jones, of the stock exchange or something like that. There are many sources of randomness, right? The hard part, is get one that you're confident that no one can game, no one can secretly predict, even when billions of dollars might be riding on that. So there are other ideas for how to do that quantum mechanically. If you have two devices that are separated but entangled with each other, then you could ask them to violate the Bell inequality, right? So demonstrate the entanglement. And it was realized 15 years ago that gives you a way to generate certified random bits. Right, but now if the devices could secretly communicate with each other, then it's no longer secure, right? So the goal with my scheme was to get certified randomness with a single device, where you don't have to have them separated. Even there are other ways to do that. There's a cryptographic scheme that was proposed by Umesh Vazirani, Zvika Brakarsky, Paul Cristiano, Urmila Mahadev, and but that cryptographic scheme, it could not be implemented using current quantum computers. You would need probably some level of error correction and fault tolerance to do it. So, can you actually get this using quantum computers that we can build today, and where the verification is efficient and where it's secure? I think that remains a challenge.
Thank you.
All right. So,
okay.
And yeah.
Yes. Thank you very much. So, Scott, we want to take you through a lightning round just for the fun of it. So there are just 6 questions, and you can use as few words as you can to just help us understand a few things about you.
Okay.
So what is the biggest misconception about the work that you do?
The biggest misconception, I would say that the biggest misconception about quantum computing in general is that it is just a magical pixie dust that's going to speed up everything, and do it in the near future, right? Rather than being based on choreographing these patterns of interference, and which is this very specialized ability, and this thing that we still have to think really hard about.
Okay, sounds good. What book are you currently reading?
What book am I reading? Well, I am reading the 5th Harry Potter book with my 8-year-old daughter. She's really into Harry Potter, so we're partner reading it right now. But also, I just got a book of classic papers in computer science, like from the ancient Greeks up to 1980. That's edited by Harry Lewis, and I've been reading that one. I've really been enjoying that.
Thank you. What is your time management trick?
I wish I had one. If anyone else has a time management trick, they should tell me, because I waste immense amount of time just getting angry at what people are saying on social media, or on all kinds of stupid things like that. And certainly over the last year with the pandemic, I've been very, very unproductive. And I hope to get back to being more productive. But also I have kids. That also makes time management difficult.
Okay, what is the best career advice you can offer to young people today?
Don't depend on anyone else to sort of tell you what to do, right? I mean, it is so easy as a student to get into this mode where you just have to solve the homework problems that someone else is giving you, right? But if you want to be a researcher, this is not just in quantum computing, but in any field, right? There is no one who is telling you what problems, to solve or how to solve them, right? That means, there are, of course, the world is full of people who you can learn from, who can tell you useful things, but you have to take charge of your own learning, right? And often, the problems that are unsolved, the reason that they're unsolved is that they're incredibly hard, right? And people have already worked incredibly hard on them. And, there's not going to be progress without some amazing new idea. And, and often the easier way to do research is to say, well, let me change the problem, right? Let me invent a new problem, that no one had considered before, but that gives us a different perspective, right? And that's something that never happens when you're doing homework in school. But that's one of the keys to research, right? And that's I think one of the most important things that you have to learn, as you progress from high school to undergrad to grad school to being your own researcher.
Okay, thank you.
Yeah.
What do you like and don't like about how quantum computing is turning out?
About what? Sorry.
About how quantum computing is turning out. What don't you like and what do you
about
like
how it's turning out? Well,
yeah.
I mean, I like, the level of interest in this field. I mean, when I was interviewing for jobs in 2007, I would get lots of people saying, well, what if the entire field of quantum computing just shrivels up and dies, and what if no one can build it and no one is interested, what are you going to do then? Right, that's a serious question, and of course, I thought about it, but in reality, the exact opposite has happened, right? People have just gotten more and more excited about it. There is more and more investment and interest. Now the downside of that is that you get bubble phenomena, right? You get the same kinds of things that happens with machine learning, or that happens with cryptocurrency, right? You get people who are entering the field, not because they're really curious about it, but just because they heard that it's a hot new thing, and that if you slap the word quantum in front of things, then it's easier to sell it to investors or something like that. And so that that's the big downside that we fight against, right? Of people who are sort of interested in it, but not for the right reasons. And of course we try to take all the curiosity that there is, which is great, and sort of try to channel it into the real issues that there are in this field.
Okay, thank you. If people wanted to get in touch with you and connect, what's the best way to do that?
Send me an email or leave a comment on my blog.
Sounds good, Scott. Thank you very much for your time.
Of course.
We
Of course, it was a pleasure.
To go
it was a
beyond.
pleasure. I apologize that we weren't able to get to all of the questions. There are a lot of great questions.
For sure.
But, thank you, everyone.
Thank you for your time. If you've got a moment, we've got a cocktail coming. There's a link that has been shared to join the cocktail so that you connect one-on-one with people who manage to attend. And I'm also not going to close the meeting right now to allow people to get the links that were being shared. Otherwise, let's meet on the cocktail. Let's keep in touch, Scott. All the best. Enjoy the holidays.
Thanks. Thanks a lot. Okay, bye.